at the poles. Right, so this was one of the topics we discussed in detail in the previous class, variation of G at the equator and at the poles. Let's do a quick revision and then let's do a practice question, past paper question. Now, the value of G normally that we know for Earth is 9.81, right? But this value is not the same on every surface, every point on the Earth. For example, let's say this is point A on the Earth, which is at the equator. And then we have point B over here, which is at the poles, the North Pole or maybe the South Pole. Now, the value of gravity is going to be slightly different at point A and slightly different at point B. The difference is very minute, it's in points, but still there is a difference. Now, why? Why does this difference exist? There are multiple reasons for it. Reason number one, the Earth is not a perfect sphere. In the beginning, I told you that we assume planets to be perfect spheres, but in reality, they are not. For example, the Earth in reality is sort of like flat, like it's an oval, flat shaped. This means that the radius of the Earth is not the same everywhere. At the equator, the radius is something like this, and at the poles, it's this. Now, you can clearly see that at the equator, the radius of the Earth is greater. And at the poles, it's slightly less because the Earth is not a perfect sphere. This variation of radius leads to a variation in the gravity value. Why? According to this mathematical formula. See, gravity, gravitational acceleration, and the radius are inversely proportional to each other. Gravitational field strength and radius have an inverse square relationship. So this means, where do you think will the gravity value be greater?
At the top.
At the poles, yes. Because at the poles, the radius is less. If the radius is less, the gravitational field strength is greater because of the inverse relationship. Okay, so this is reason number one. Reason number two, density of the planet is not constant. Or in other words, you can say that the mass distribution on Earth is non-uniform. Why? See, the Earth is made up of different materials. The Earth is made up of land, and then there is water. Then there are a lot of radioactive materials. We have metals. So see, every part of the Earth has a different density. So the mass distribution is non-uniform. Because of that, the gravitational field strength value is also non-uniform. Reason number three, influence of other planetary objects. Example, moon. Yes, the Earth in reality is not isolated. There is some influence coming from the moon. And finally, the third reason, which requires a little deeper understanding, is the planet's spinning effect. Centripetal force is zero at the poles. Okay, what does this mean? At the poles, centripetal force is zero. But why? It's because at the poles, the orbital radius is zero. Now, what does orbital radius mean? Let me show you a little animation. See, this is the Earth. Let's make it a little transparent. Now, let's pause the video here. Okay. Now, this is Singapore, which is near the equator. And this is Oslo, which is near the North Pole. You can clearly see that the orbital radius for Singapore is greater. And as you're moving up towards the pole, the orbital radius is decreasing. Not, let me repeat again. The word orbital radius and the radius of the Earth, these are not same things. Orbital radius means the radius around which that object is rotating, like the object is undergoing circular motion. So the radius of the circular path is called orbital radius. So you can clearly see that as you move up and up towards the poles, the radius of the circular path, which is called orbital radius, is decreasing. Now imagine you are exactly at the pole. The orbital radius is ideally going to be zero over here. Now, if the orbital radius is zero, centripetal force is also zero because we know that the formula of centripetal force is mv square upon r, or you can even take this one, mr omega square. In both the formulas, you have radius r. If r is zero, then mathematically fc also becomes zero. So at the poles, orbital radius is zero. Because of that, centripetal force is zero. Okay. Now, if I construct an equation, see, this is the Earth at the poles. Let's draw the forces. You have downward gravitational force. You have upward normal contact force. So the centripetal force, which is the resultant force, is supposed to be equal to gravitational force minus the normal contact force, right? Minus because the forces are in opposite directions. Okay. Now, centripetal force is zero. I just discussed that. So you're left with gravitational force, if I take normal force on the other side, equals to normal force. So see, gravitational force equals to normal force. Now, if I try doing the same sort of concept calculation for the equator, let's see what happens at the equator. At the equator, you have orbital radius, right? It's not zero. You do have an orbital radius. So that means you do have centripetal force. So the equation is the same. Centripetal force equals to gravitational force minus normal contact force. Let's rearrange the equation for normal contact force and see. The normal contact force is equal to gravitational force minus centripetal force. Normal contact force equals to gravitational force minus centripetal force. This equation is for the equator. And what was the equation for the poles? Normal contact force equals to just gravitational force. So you can clearly see where is the normal contact force greater? At the poles. So that's why the gravitational field strength at poles is greater. Or you can say that, imagine, for example, you are standing at the pole and then you travel all the way to the equator. Your weight will be slightly lighter at the equator, and your weight will be slightly heavier at the poles. Why weight? Because, of course, weight depends on gravitational field strength. Remember, weight is equal to mg. Right? So these were some reasons that we discussed in the previous class. I just completely revised it again. Now let's do a question related to this concept. Yep, please read it out. Let me know when you're done.
Done.
All right. So you are supposed to state some formulae. You're supposed to give an expression or the formula in terms of the following variables: capital M, small m, capital R, omega. Let's quickly identify what these are. Small m is the mass of this small object that is resting on the equator of the planet. Okay, capital M is, I assume, the mass of the planet. Yes. Capital R is the radius of the planet. And omega, what is omega? It is the angular speed of the planet. State a formula for the gravitational force between the planet and the object. Okay, do you remember a formula for gravitational force?
Uh, what do you call it? The gravitation, gravity into the mass um,
The other mass,
into
basically the Newton's
yeah,
law of gravitation.
yeah, upon the radius square.
Yes, perfect. Capital G, which is gravitational constant, multiplied by mm, the two masses, the mass of the planet and the mass of the small object, divided by r square. Make sure you use capital M, small m, capital R. All right, perfect, done. Number two, the centripetal force required for circular motion of the small mass. Okay, any formula for centripetal force, but make sure it includes these values. So which one?
The small mass into the radius into the omega square.
Perfect. Make sure it's small mass. Correct. M, capital R, omega square. Correct. Number three, the normal reaction exerted by the planet on the mass. Okay. Now, just over here, when I was telling you about the value of G at equator and poles, remember I drew this little diagram. So let's, of forces. So let's draw the same forces over here. Now, at this point, you have gravitational force, which is, of course, towards the center of the planet, Fg. And then you have normal contact force, which is like this. Okay, now let's construct an equation. The resultant force, which is centripetal force, is supposed to be equal to gravitational force minus normal contact force, correct? But we want an equation for normal contact force, so let's rearrange it. Normal contact force equals to gravitational force minus centripetal force. Am I correct?
Right.
Perfect. So that's it. This is your answer. But of course, you will not use the F. Instead, you're supposed to use the
We
variables.
just yeah minus the first answer and the second answer.
Absolutely. First answer minus second answer. G M M R square minus M R omega square. Done. All right, part B. Explain why the normal reaction on the mass will have a different value at the equator and at the poles. 2 marks. Okay, I explained everything. What do you think? How will you word it over here?
Because at the poles there is no circular motion. So like the what do you call it? The radius is zero, and I don't know like how to explain it.
Hmm. Okay, you are right. Centripetal force is zero, but please give the reason. Why? Why is it zero? Because near the poles, the orbital radius decreases. See, let's write it something like this. As the mass moves away from the equator towards the poles, the orbital radius decreases. In this expression, mention the expression. And if this decreases, centripetal force decreases, you can say. And hence, the question is asking you what happens to the normal reaction force. So what was the equation at the one that we constructed? Centripetal force equals to gravitational force minus normal. Rearrange for normal. Normal equals to gravity minus centripetal force. So if the centripetal force keeps on decreasing and decreasing, what will be the effect on the normal contact force? Mathematically, look at this equation. If this is decreasing, what will happen to n normal?
And will increase.
It will increase because imagine you're now subtracting it with an even smaller and smaller number. So overall, the normal contact force should increase. So your answer should be something like this. where you've mentioned all the reasons, even the mathematical expression. 2 marks. Clear?
Yes, miss.
Part 2. The radius of the planet is 6.4 into 10 power 6 meters. It completes one revolution in 8.6 into 10 power 4 seconds. Calculate the magnitude of centripetal acceleration at the equator. Okay, let's use the formula for centripetal acceleration. Hmm, maybe this one, r omega square. Why this one? Because notice I've been given time period. So instead of omega, I can write
2 pi
2
upon time
pi
period.
upon time period. Perfect. Okay. The radius is given. Yep. And the time period is also given. Simple solution. You should get your answer, which is 0 after solving 0.034. All right, done. Moving on. This was a simple one. Part 2. Now you need to calculate the same thing, same question. You are supposed to find centripetal acceleration, but now for one of the poles, meaning either north or south pole. Okay, what do you think? The formula, maybe if you try using the same formula.
It's gonna be 0.
Yes, perfect. No calculation at all. It's zero. Why is it zero? Because the orbital
Because
radius is zero exactly at the poles. So there is no circular rotation, no centripetal force. If you want, you can maybe write it down. A is equal to r omega square. Zero times omega square is zero. But this is actually not really needed. It's just a 1 mark. You could just write zero here. This will give you marks. All right, finally, part C of the question. Suggest 2 factors that could, in the case of a real planet, cause variations in the acceleration of free fall at its surface. We just discussed all these reasons. 1, 2, 3, 4. You could mention
the
any 2 of
the
them.
non-spherical shape of the
Perfect.
planet
Okay, number
and
1.
the unconstant density.
Perfect.
I mean, non-uniform.
Okay, yes, one more thing I would like to add is mentioned like in the first part you said that the non-spherical shape of the planet. Further add, what does that have to do, how does that affect the gravity? Mention that because of the non-spherical shape, non-perfect sphere, the value of radius varies, and that's why the gravity varies. I mean, this was the keyword. I think if you just mention the not perfect sphere, you might not get a mark. All
Got it.
right, got it. Perfect. So this was a question on this topic. Let's now maybe move on to gravitation potential. So in the last class, we discussed the definition for gravitational potential, the formula, and also we discussed a very important point that why is gravitational potential negative? Although it's a scalar quantity, but then why do we put a negative sign? These were the reasons. If I highlight the keywords, you're supposed to say that it's because work is done by the gravitational field, and gravitational field is attractive in nature, right? It's always attractive, it's never repulsive. So the work done represents a loss in energy. And that's why to signify this loss, we insert a negative sign. And one more thing, gravitational potential at infinity is zero. I basically, let me highlight it with different colors. I basically just highlighted all the key points that you need to write in case an exam question asks you, why is gravitational potential negative? This is actually a very common past paper question that comes as a 2 mark question, even as a 3 mark question. So these are the keywords that you will usually find in the marking scheme for this question. Okay, so we also saw the graphs for gravitational potential. Let's quickly have an overview. Since you can see according to the formula that potential and radius are inversely related, so the graph for potential versus radius is also inverse. And it's a negative inverse. So you need to draw it in the negative gradient, negative quadrant, sorry. And one more thing about this graph is that the gradient of this graph represents small g. It represents gravitational field strength. Why? It's because gradient is supposed to be equal to mathematically y-axis divided by x-axis, correct? What is the y-axis in this graph? It's potential. What is the x-axis? It's radius. Okay, let's substitute the formula for potential, which is negative gm upon r divided by r. If you take the r up, simplify, you get negative gm upon r squared. And this is the formula for small g. So the gradient of a potential versus radius graph gives us gravitational field strength, the negative gradient actually. Okay, and then finally in the class, at the end of our last class, we talked about escape velocity and this graph also. This is the combined graph for gravitational potential. Just like we saw the combined graph means when the Earth and moon both are taken into consideration. Normally, we assume Earth to be isolated, but if we don't assume it to be isolated, the combined graph looks something like this, the one that I just highlighted with yellow. This is the combined or resultant graph. And both of the individual graphs for the moon and Earth are in the same quadrant. They are both, for example, below the x-axis. It's because both of them are negative. And remember, potential is not a vector quantity. It's a scalar quantity. So you don't have to worry about directions. Now, over here, you can see that at this point, gravitational potential is maximum. The resultant potential is maximum. Now, what's so special about this combined graph is that imagine at the surface of the Earth, you have a rocket and you're trying to launch the rocket and land it on the surface of the moon. You need to provide enough energy, right? So that the Earth can escape the Earth's gravity, so that the rocket can escape the Earth's gravity and reach the moon. But scientists only need to provide enough energy for the rocket to just reach this null point. Null point is the point where the potential is maximum. After this point, why do we not need energy? Because the rocket will move itself due to the gravitational pull of the moon. So in this situation, the escape velocity needed by the rocket is less due to the influence of the moon, because you only need to launch the rocket all the way till the null point. After that point, it will move on its own because of the pull of the moon. Hmm. Okay. Similarly, in exam questions, you might also be asked to find the change in gravitational potential or change in gravitational potential energy. What is gravitational potential energy? The formula for gravitational potential energy is potential multiplied by mass. So potential was gm upon r, just add an m. So gmm upon r is the formula for potential energy. Anyways, this is simply the difference between them. See, do not forget the negative signs. Potential is negative. So this negative negative eventually becomes positive. If you simplify, you get this formula for the change in potential energy. If you don't want to memorize this one, it's fine. You can simply subtract them on the spot. Okay, so let's now look at a question related to gravitational potential. Okay, this one. Number one, define gravitational potential. So the proper definition for gravitational potential is this. It
Weight per unit
is,
mass.
no, this is, did you say weight? It's work done per unit mass. Work done per unit mass, but that's not it. If you just say work done per unit mass, you will get 1 mark. It's a 2 mark question. Work done per unit mass in doing what? In bringing the mass from infinity to a defined point. I explained this definition in the previous class. See, for example, this is a point, a very far away point. So let's call it an infinite point. And then let's call it point A. And then I am trying to bring this mass to point B. So in order to move the mass from point A to point B, work is to be done on the mass. So work done per unit mass in bringing a mass from infinity to a defined point. This is your complete 2 mark definition. Done. Part B. Explain why the value of gravitational potential near an isolated mass is negative. 3 marks. So let's just write down all our key points that I highlighted. Number one, gravitational force is attractive, so work done is by the field and it represents loss in energy. And at infinity, potential is 0. See all the 3 keywords. The first keyword is this. Gravitational force is attractive. The second keyword is work is done by the field. So it represents a loss in energy. And the third key point is potential at infinity is 0. These were your 3 points that give you 3 marks. Now, part C. The Earth may be assumed to be an isolated sphere of radius 6.4 into 10 power 3 kilometers with its mass of 6 into 10 power 24 kilograms. An object is projected vertically from the surface of the Earth so that it reaches an altitude of this. Calculate for the object the change in gravitational potential. So you need to find change in gravitational potential. The object is being launched from the Earth's surface to a certain altitude of this. So that's why they're asking change, because there are 2 points. The first point is the surface of the Earth. See, this is the Earth. The mass is, let's say, right now at the surface of the Earth over here. The mass is to be launched up to a certain height of 1.3 into 10 power 4 kilometers. This is point B, let's say. So, yep, that's it. You need to find the change in potential. Yes, let's use the formula. So the formula for potential was, change in potential was, um, if I directly write down the simplified version, it's Gm 1 upon R1 minus 1 upon R2. What is R1? R1 is supposed to be the first point, which is, what is the first point? It is the surface of the earth. So at the surface of the earth, you take this as your value. 6.4 into 10 power 3. Okay, and what to do for R2? A lot of students made a mistake here and they took the R2 value as 1.3 into 10 power 4. You need to add this value to the radius of the earth. See, because in this formula, gm upon r, in this formula, r is the distance all the way till the center of the planet. So this r1 is supposed to be equal to the altitude, let's call it h, plus the radius of the earth. So basically 1.3 into 10 power 4 plus 6.4 into 10 power 3, which should give you 1.94 into 10 power 7. Anyways, that's it. You solve and you will get your answer. Clear?
Yes, miss.
Part 2, the speed of projection from the Earth's surface, assuming air resistance is negligible. Speed of projection. Okay. In the last class, we did a little derivation when we were talking about escape velocity. Let me bring back that derivation. See, what is escape velocity? Let me quickly recall it for you. It is the minimum velocity required for an object to escape from the surface of a planet. Like imagine you're trying to launch a satellite. So that satellite needs a certain minimum velocity to be able to escape the surface of the planet outwards towards infinity. That's called, simply speaking, that is called escape velocity. So in this question, they're actually, if you think about it, they're talking about escape velocity. They haven't used the word escape velocity exactly, but don't you think this is escape velocity? See, they're talking about the speed of projection. What was happening above, if I go back to the question, what was happening over here? An object was being projected from the surface of the earth. So that object is basically trying to escape the surface of the earth, right? So it needs a certain minimum velocity. So they're asking, that's the question. They're asking you the escape velocity. So we did this derivation in the last class, um, and we reached this formula. You do not need to memorize this formula. Instead, if you even look at the question, it's a 5 mark. No, I think the marks are distributed. Sorry, this is 2, and then this is 3. 5 is the total. So anyways, it's a 3-mark question. Let's say you memorized the formula and you used it directly in the question. You will not get complete marks because I think the steps carry marks. The derivation steps carry marks in this question. So anyways, let's look at the derivation. Very simple. The derivation is supposed to start from the concept of a conservation of energy. See, as an object moves up, uh, away from a planet into the outer space, what is happening to the gravitational potential energy? It's increasing. Why? Because the height of the object above the surface of the earth increases. We have learned this since elementary classes, since O levels, that gravitational potential energy depends on height. It depends on the position of an object in a gravitational field, right? So as you're moving up, gravitational potential energy increases. And that's why, consequently, in order to conserve energy, kinetic energy must decrease. So that's why it says loss in kinetic energy and gain in gravitational potential energy. All right, let's now substitute the formula. The formula for kinetic energy is simply half mv squared. The v over here is the escape velocity that we are trying to find. And the gain in gravitational potential energy is phi m, potential multiplied by mass. Now the masses cancel out from both sides. This, this is an important point which gives us proof that the escape velocity does not depend on the mass of the object. So it doesn't matter whether you're trying to launch a heavy object or a lighter object, the escape velocity is independent of the mass of the object. All right, let's continue. So now you're left with, on the right side of the equation, you're only left with change in potential. So change in potential simply means final potential minus initial potential. What is the final point? We are assuming that the final destination is an infinite point. So the formula becomes Gm upon infinity, and anything divided by infinity is 0. Simplify, simplify, and that's how you're left with this. So, I mean, the derivation is simple, but you just need to remember where the derivation starts from. Like, if you remember where the derivation starts from, you can just go on. The next steps are just mathematical. You can work your way out, but only if you remember where the derivation starts from. So this is a little maybe helping point for you, that you have a lot of derivations in A2 physics. All right. So you can just remember where all the derivations start from. If you know that, you'll have a good head start, and then you can work your way down and do the mathematical part yourself. Yeah, okay, that's it. This is the formula. And then there is another formula, another version of this formula in terms of small g, right? This is just one extra step in case the question asks you to write down the formula in terms of small g. See, this formula is in terms of capital G. In terms of small g, just, gm equals to small g r square, substitute it, and you get this. So you're supposed to do this exact thing in the question. Start with this. Kinetic energy equals to the gravitational potential energy loss and gain. Substitute the formulas and find, what are we finding? This V. Okay, you don't need to actually do the entire formula in this question. See, you already know the value for this change in potential. Here it is. We just calculated it above. So half V square equals to the value 4.2 into 10 power 7. Solve, solve, and you get velocity. Done. I hope it's clear.
Yes, miss. Yeah.
All right, perfect. All right, moving on towards the next topic, satellites. Now, in the topic of gravitation, you're supposed to know about a few types of satellites. Number one is a geostationary orbit, or you can say a geostationary satellite. These are satellites that have the following properties, three properties. Okay, number one, these satellites move from west to east. What's so special about moving from west to east? West to east is the same direction as the Earth's spin. The Earth, see, the Earth has two motions. I hope you know that. Number one, the Earth revolves around the sun. right? This is the sun, this is the earth. Of course, all the planets revolve around the sun. Other than this, the earth also spins about its own axis. So that spinning, direction of that spinning is from west to east. So the geostationary orbit also moves from west to east. Okay, this is the first property. Property number two, geostationary satellites have the same orbital time period as the Earth's rotational time period. By rotation, I mean the spinning period. The Earth takes 24 hours to spin around its own axis, right? And how much time does the Earth take to complete a revolution around the sun? An year, 365 days, right? So the time taken to spin around its own axis, I'm talking about the spinning, that takes 24 hours. So the orbital time period for the geostationary satellite is the same as the Earth's rotation, 24 hours. This means that, for example, this is our Earth, and this is the geostationary satellite that is revolving around the Earth. The time taken for the satellite to complete one revolution is going to be the same as the Earth's rotation, which is 24 hours. So if the orbital time period is the same, that means their angular speed is also identical. Because remember, angular speed equals to 2 pi upon t. If t is same, angular speed is same. All right, number three. The geostationary orbit has an equatorial orbit, meaning, look at this diagram. I've drawn this. Do you see this purple line? This is the orbit of the geostationary satellite. It's always going to be above the equator. The word in exams, you can simply use the word equatorial orbit. But for your understanding, what does it mean? It means that the satellite always remains above the equator. And that's why it's given this name. Why is it called geostationary? The word geo means earth, and the word stationary, you know what stationary means. Now, why do we call it geostationary? It's because since the satellite is always at the same point above the earth, it's always above the equator, it seems like it's stationary. Do you get it? See, um, this is the earth, this is the satellite. The satellite is revolving around the earth in an equatorial orbit, number one, meaning it's always going to be above the same point. And number two, it also has the same period as the Earth's spin. So if a scientist tries to view the satellite from anywhere on the Earth, he'll always see that the satellite is at the same point. Do you get it? It has something, this has something to do with physics, relative motion. The Earth is also spinning with the same angular speed and the same period. And this satellite is also moving with the same period and the same angular speed. So it seems like from the Earth, it seems like the satellite is not moving, it's stationary. So that's why it's called geostationary satellite. So that's it. You need to just know these three properties about a geostationary satellite. This can come as a simple question, like maybe they could simply ask you the properties, or it could come as a slightly different question, like, you know how A-level questions are slightly twisted. For example, I have a question in mind. You were given a planet, it wasn't Earth, it was, let's say, Mars. Okay. So this means that this concept of geostationary orbits doesn't only apply to Earth. It could apply to any planet. So the question was like, they said that there is a moon revolving around, there is a satellite revolving around Mars. They gave you the time period of Mars, and they said that this satellite is always seen above the Mars at the same point. They didn't mention equator. They just said that they just said that the equator is seen at, sorry, the satellite is seen at the same point above Mars. Mention two other properties about this satellite. So see, automatically it should come to your mind that if the satellite is seen at the same point above Mars, this is one of the properties of a geostationary orbit, a geostationary satellite. So the other two properties are going to be, you're going to say that this satellite moves in the same direction as Mars. Don't say west to east because we don't know the direction of motion of Mars. See, the concept is that the satellite is supposed to move in the same direction as the spin of the planet. Since Earth spins west to east, that's why the geostationary orbit for Earth also spins west to east. If the planet Mars moves in maybe east to west, then the satellite will also move east to west. So it's safe to say that the movement of the satellite is in the same direction as the Mars spins. Number two, you can say that the orbital time period for the satellite is the same as Mars. Again, don't make a silly mistake. Do not say 24 hours because 24 hours is not the time period for Mars, right? It's the time period for Earth. So, yeah, that's it. This was a simple little topic about geostationary satellites. One more thing, some examples you need to know. Some uses. Why are geostationary satellites used? They are used for mostly telecommunication transmission. Example, radio broadcasts, television broadcasts, weather forecast. So geostationary satellite is responsible for all of this. Okay, what's a disadvantage of a geostationary satellite? Since the orbit is equatorial, remember, it cannot give you coverage to the polar regions. The orbit of the geostationary satellite is only above the equator. It is unable to give coverage for the poles. So this is a disadvantage that could come as a question. Now, next, GPS, Global Positioning Satellite. The orbit of this satellite is at a 45-degree angle, something like this. So what's the advantage? The advantage is that you can monitor both the equatorial regions and the polar regions. Because of its 45-degree tilt, this satellite is able to monitor all the regions, equatorial as well as polar regions. I think that's it. You just need to know about these satellites.
Got it.
All right, perfect. Now a few more little derivations. Kinetic energy of a satellite. Okay, again, let's try to memorize the derivation. But remember, I told you just try to know where the derivation starts from, then you can work your way yourself. So this derivation is supposed to start from the concept that centripetal force equals to gravitational force. Let's substitute the formula mv squared upon r equals to gmm upon r squared. The r cancel out. One of the r cancels out from here. This r cancels out. The mass can also cancel out. If you notice, the small m can also cancel out, but we will not cancel it. The reason we are not canceling it is, let's look at it ahead. Now you're left with mv squared equals to gmm upon r. What are we deriving exactly? What is the derivation for? It's for kinetic energy. What's the formula for kinetic energy? Half mv squared. I need to somehow bring half mv squared over here. So I'm going to multiply by half on both sides. I can do that, right? Mathematically. So multiplying by half on both sides, and that's how I got half mv square. So see, this is the reason why we did not cancel out small m in the very beginning. Otherwise, you would not have been able to get half mv square. So finally, this half mv square, which is kinetic energy, equals to half gmm upon r. Okay, done. Next, gravitational potential energy. Okay, the derivation is nothing special. You already know potential energy is supposed to be equal to potential multiplied by mass. So gmm upon r, but negative, remember, because potential is negative. Okay, this means gravitational potential energy is negative, but remember, kinetic energy is always positive, always. And finally, total energy. Now, this means the satellite has two types of energies. It has kinetic energy and it has gravitational potential energy. So, if I try to find an expression for the total energy, it's going to be kinetic plus potential. Just substitute the formulas, the ones we just derived, half gmm upon r plus negative, do not forget the negative of potential, negative gmm upon r, simplify, simplify. What did we do in the next step? I took out gmm upon r as common. I factored it out, and you're left with half minus 1. What is half minus 1? It's half, negative half actually. So this is your final expression for total energy. So these are the energies for satellites: kinetic energy of a satellite, gravitational potential energy of a satellite, and then the total energy of a satellite. Okay, these are some conceptual points over here. See, what is the relation? Look at this formula. What is the relationship between total energy and radius? Inverse. But again, don't ignore the negative sign. It's a negative inverse relationship. So what does this mean? If I say that the radius decreases, what should happen to the total energy? I've seen most students make this common mistake that if the radius is decreasing, then they say that the total energy should increase because of the inverse relationship. But no, remember, it's a negative. That's why the negative is very important. It's a negative inverse relationship. See, imagine your total energy will now become more negative. And I hope you know mathematically, the greater the negative number is, the smaller the value it holds. For example, I have a number -5 and then I have -1. Which one is a greater number in value, in terms of value? -1 is greater, -5 is smaller, right?
Right.
So this means that in negatives, if your number increases, meaning if it's becoming more and more negative, like -5, -6, -7, it means it's actually decreasing, right? So this was a very simple thing, but yet I've seen students make this mistake. So because of the negative sign, as the radius decreases, the total energy also decreases. Same thing for gravitational potential energy. The formula for gravitational potential energy is this. Again, what is the relationship with radius? It's a negative inverse relationship. So same concept. If the radius decreases, then the potential energy must also decrease. But for kinetic energy, there is no negative sign. It's a simple inverse relationship. So if the radius decreases, then the kinetic energy should increase. Call it.
Got it.
All right, perfect. So, well, We're actually done with the topic of gravitation. In the next class, tomorrow's class, we will do some, we'll keep the entire class, tomorrow's class, for past paper practice on gravitation.